All right, good morning. Thank you. Okay, so exam tomorrow. Make sure you look up where you're going. And once again, if you're in Alex Porter's class, now is a good time to find out where Lin Ho is and how to get there and how much time it takes to get there. So please do that before tomorrow night. So once again, 6:30, go to the right location. And just like last time, 12 questions, 8 points each. You get 4 points for showing up. Okay, let's get started with the review then. Got quite a bit of things to go over. All right, so let's start with the centroid stuff. Going to go all the way back to centroids. And let's do this by example. Okay, we got some kind of region here, 2 minus x squared and x squared. And we're looking for the center of mass of this shape. All right, so let's sketch this. This one is easy to see. It's simply x squared. So parabola with the vertex at the origin. The other one is an upside-down parabola with the vertex at 2. Okay, so we're looking for, if you're looking at this shape here, where would you place your finger underneath that plate so that you could balance that plate with no wobbling, no turning over? And it's pretty easy to check that these two things intersect at plus or minus 1. Very, very easy to check. And we need two things, of course. Remember, to find the x location of the center of mass, we will find the moment about the y-axis divided by the area. And then for the y component is mx over a. Okay? All right, so who remembers the formula for mx? What's the general formula for that? Plus or minus? Yeah. So how about let's do top plus the bottom, and then top minus the bottom, the x, right? You go halfway, go to the average between the top and the bottom, multiply by. This is essentially the area. Okay, what about my? Somebody else? How is that different? Yeah. Times this stuff, right? Good, very good. And there's actually also a density in both of these equations. But normally the density shows up in area also. So usually we just throw that density out of the way. Okay. Now before you do any calculation, look at the shape you're dealing with. I can tell without doing any calculation I can tell that the x component of the center of mass has to be 0. Can you see why that's the case? Yep. It's symmetric left and right of the y-axis, right? Same area on the left and right. So this thing has to be, the centroid has to be somewhere along the y-axis. Now the y component is a little bit harder to see. It's going to be somewhere on the y-axis, and we're going to have to find that just to be absolutely sure what it is. So let's find y bar. Okay, I'm taking that formula here, and then integral a to b minus 1 to 1, average between the top and the bottom. So top is this stuff here. The bottom one is x squared. And then top minus the bottom, dx. And then downstairs, we have just the area. That's easy. Minus 1 to 1, top minus the bottom. All right? Okay, simplify. Notice here the x squared will cancel. So I have a 1/2 and a 2, and that reduces to a 1. And then this right here is 2 minus 2x squared. And we got kind of lucky here. Downstairs, it's also 2 minus 2x squared. Okay? So normally you would carry out the integration, which it's not really hard to do here. But in this example I did here, these turn out to be exactly the same thing. So whatever they turn out to be, I know the ratio is going to be 1, right? So now I know where the center of mass is. It's going to be somewhere over here. And it's got a coordinate of 0, 1. All right, so the key equations are here. You have to know these equations. You won't get these on the exam. Question? You got it? Okay, good. All right. Okay, so that's the centroid stuff. Let's get into sequences. And again, let's do this by example. Now remember, sequence is simply just a list of numbers in a specific order. If I put in n equal to 1, then the first one that comes out is going to be negative 4 over 6. The next one is minus 3 over 7, minus 2 over 8, minus 1 over 9, 0, 1 over 11. And the pattern is pretty clear after that. The denominator keeps getting bigger, 1 at a time. So that's a 0 over 10, really. And then upstairs also gets bigger, 1 at a time, starting at minus 4, minus 3, and all the way up. The first question we want to ask here is, does the sequence converge? So what does it mean when a sequence converges? What approaches the final number? So the term down the road. Right? So how would you find that? Okay, so we take a limit, right? That's how you would do that. Good. So we do a limit, n goes to infinity, a n, and this has to be equal to a finite number, right? If it turns out to be some finite number, then we say the sequence converges. And here, this is pretty easy to see. When n gets sufficiently large, the minus 5 and plus 5 don't matter, and we have an n over n. That takes me to 1. So now we're seeing that if I keep going down this list, eventually these numbers will get closer and closer to 1. What about the boundedness of the sequence? What does it mean when a sequence is bounded? Yeah. And does my sequence here have those two things? Yeah. So, first of all, has a smallest term and a biggest term, right? Here, the smallest one is the one here. These things are all getting bigger as they go on. So negative 4 over 6 or negative 2 over 3. What about the biggest? 1, yeah. If we could reach infinity at the right end, we would get to 1. Okay? The terms approach 1 as we keep expanding the sequence. What about the increasing and decreasing question? This one is pretty easy to do by inspection. The terms are increasing. But in general, a good way to find that is to take the derivative. Okay, so we imagine that we get the terms of that sequence out of this function here. If the function is increasing, then the sequence is increasing. If the function is decreasing, then the sequence is decreasing. Take the derivative. And we end up getting 10 over x plus 5, the quantity squared. So I use the quotient rule here. It's a very simple process because both of the derivatives are 1. And now the function that gave us the terms in the sequence, this function is the derivative is always positive, so this function is increasing. So therefore, the sequence is also increasing. Okay? Questions? Okay, good. Now let's do series. Let's start with geometric series. So these are the things that start with a term A, and then every subsequent term has the same ratio. So it keeps going. Right? And we know this turns into A over 1 minus R. As long as the absolute value of R, the common ratio, is bound to be strictly less than 1. Does it look blurry to you? Okay, let me try to fix that. How about that? Well, the light is on, so it should have been autofocusing in the first place. Anyway, we got it. Okay, should have told me. It doesn't look so bad here, but all right. Okay, so there's our things we can deal with the geometric series. Now let's do this example here. This one is a little bit complicated. If you can do this one, you should be in good shape as far as geometric series go. Here I want to find the sum of that series. Now the first thing you notice here is it doesn't look quite like the simplest form that a geometric series is supposed to have. But because these things are added together, it's worth trying separating them out. Now I broke apart the numerator, and each one is dividing by the same denominator. So I have an infinite series. The first one is minus 1 to the n over 3 to the n. The second one is 2 to the n minus 1 over 3 to the n. And both of these are geometric series. The first one is pretty clear. The second one here write 2 to the n minus 1 as 2 to the n times 2 to the minus 1. And that's equivalent to 2 to the n over 2. Now in the second group here, then we have 1/2, right, from my over 2. And then I have 2 to the n over 3 to the n. Or 2 over 3, the whole thing to the nth power. Okay? Now each of these two, you can find the sum using the regular sum formula. Now what is the term a in the first series? What is the number a? 1. That's the first term in the series. Well, wait a minute. Is it 1? Right. The a is the first term in the series, right? So this series starts at, it's minus 1 over 3 plus 1 over 9, and so on. The second one here is 1 over 2 times 2 over 3, so that's 1 over 3 plus 1/2 times 2 square over 3 squared, and so on. So the first of each of these is the number a. Okay, so the first series has a being minus 1 over 3. And then the common ratio is minus 1 over 3. The second series has a equal to 1 over 3. And then the common ratio of 2/3. So we get negative 1/4 plus 1, or 3/4. Okay, questions? Good? All right, good. Now let's look at all the convergence tests that we have seen. The first one you always want to try first is the divergence test. If the last term doesn't go to 0, the series is going to diverge, and therefore nothing else to do. But if the limit goes to 0, that doesn't mean anything. It means that there's more to find out. And then we have the p series, 1 over n to the p He is the exponent of n. Okay, so what does n have to be for that series to converge? Greater than 1. Can it be 1? No. 1 gives us the harmonic series, which we know is divergent. Okay, good. So that's pretty easy to know. And the geometric series, we'll look at that already, so I'm not going to mention that again. What about the alternating series? How do you know an alternating series converges? So essentially this guy here, right? Good. Very good. So first, this thing, basically the divergence test again. And then the second condition is Bn plus 1 is less than or equal to Bn for some n. Well, let's do for n bigger than or equal to something. Basically, the first few terms can violate that condition. But after a while, it has to start decreasing all the way through. It's okay to have a few finite terms not doing this. Perfectly fine. But eventually, you want that to happen and stick with that behavior. And we have a way to estimate how accurate the partial sum is. Only for alternating series. Okay, remember the accuracy is no worse than the magnitude of the first term that you ignore. Let me give you one example. So here we have minus 1 over n squared, and these things come out of that. The second partial sum is what happens when you add up two terms. And then the first of the terms that you ignored is an indication of accuracy. So this one is no more than absolute value of the next one from the true sum. Okay, so this is no worse than 1 over 9 overestimate or 1 over 9 underestimate. It's within that number of the true sum, whatever that true sum happens to be. And the more you include, the better the estimate is. And this is only true with alternating series. Every other series we've looked at, this is in general not true. Yeah?
You said that S2 is the first feature on 2. If you started the series at 0,
Yeah.
would it be n equals 0, n equals 1, or n equals 1, n equals 2?
You need to count how many you're adding no matter where you start.
All right.
So I could start at 5, and then I would count the first 2, regardless of what I started with. Okay? Questions on this? Good. Okay, now the next one is the ratio test. And I have a very important thing to say about the ratio test. Now we know that if the ratio is strictly less than 1, then the series converges absolutely, which is a stronger type of convergence. So if that happens, the series converges. If the ratio turns out to be exactly equal to 1, then it's inconclusive. It does not mean the series does not converge absolutely. Yeah, that's a hard sentence to read. It's got two negatives in here. What it means is simply it doesn't know. Okay? So the ratio equal to 1, this is a very, very polite way to say you wasted your time. I can't tell you anything you didn't already know. This is a waste of time. It does not mean the series does not converge absolutely. So I know a few people have been seeing this 1 and then automatically say the series can no more than converge conditionally, which is not true. For example, let's look at a series we just looked at. If I apply the ratio test, then right away you can see that when n becomes large enough, these two are roughly equal. So this thing is going to give you a ratio of 1. But that series right here still converges absolutely, because if I take the absolute value of every term, which is what absolute convergence means, then I get a good old convergent P series. Right? So even though the ratio test gives me a 1, it still converges absolutely, therefore converges. So again, just because you see a 1, 1 doesn't mean anything whatsoever. It means that that line should never have been there in the first place. Something else is needed to give you further information. Yes? Conditionally. Okay, so that's a good question, and I have an example to answer that. Conditionally means it converges, but not absolutely. And here's a perfect example of that. Right? This thing converges. We know that. It passes the alternating series test. But it does not converge absolutely. It's a harmonic series that always diverges. So the series itself converges, but the absolute value of the series does not. That's a conditionally convergent series. Okay? All right, so let's continue with the tests. Root test. If the nth root of the absolute value of an is less than 1, just like the ratio test, this thing converges. And finally, there's the integral test. Basically, if you integrate whatever the series is summing up, and if it converges, then the series is going to converge. All right. Now, you need to be able to find the interval or the radius of convergence of a power series that we give you. And let's use that as an example. And the best way to do that is to use the ratio test. And we know if this thing is less than 1, strictly less than 1, then the series will converge. So now we can find out what x has to be for that series to converge. And with this one here, we see that that goes to 1. So absolute value of x is strictly less than 1, which means for now we know it's going to converge within these two places. And that's going to have a radius of convergence of 1. And then you also have to remember to check the endpoints by taking those numbers into the series. And then look at what you get. Right? You end up with one of the series that we have already seen, and then you can make a conclusion about the endpoints. The radius part is easy. That's not affected by the endpoint. But the interval is affected by the endpoints. You have to know this one for the exam. But we'll give you things like sine of x, cosine of x, e to the x, and the inverse tangent of x if the problem requires you to use one of them. But this one you have to know. And you also have to know the definition of Taylor and Maclaurin series. So this is Taylor. Maclaurin is the same as Taylor, except A is equal to 0. Okay? All right. Now I'm going to do a problem that this came from one of the old exams that a few people have asked me about. So we get this function here. And somehow you're supposed to find out the fifth derivative of this at 0. So I think this is from the fall 2014, one of the later ones. All right, so the thing you don't want to do is differentiating this 5 times. That's definitely not the way to do it. There's not enough time to do it. Okay, so that's not a way to do it. Instead, what you want to do is to start out with a power series of sine, which we will give you. Okay, so here's the power series of sine. Then you put together a power series of sine of 3x. And you just simply replace every single x with 3x. Right? Then to get x squared sine of 3x, you multiply every single term by x squared. So that becomes 3x cubed. And then this first one, you get 3 cubed x cubed times 2 more factors of that. So that's going to give you x to the 5th. Okay, so this is equal to 3 cubed x cubed. And this bumps up to a 5 because we're multiplying everything by x squared. And then the next one is the same thing. It's plus 3 to the 5th. It already had x to the 5th. It gains 2 more. And so on. We still want to find out the 5th derivative. So now you got to remember the definition of Maclaurin series. Right? So that's the basic definition of a Maclaurin series. To find out what the 5th derivative is, it shows up in the term containing x to the 5th. So this guy right here must be equal to this. Because that's the term in the Maclaurin series of that we put together by doing this, that contains x to the 5th. Okay? So now you compare these two, we see that negative 3 cubed over 3 factorial must be equal to the 5th derivative at 0 over 5 factorial. So therefore, this thing that you wanted to find must be equal to negative 3 cubed times 5 factorial over 3 factorial. And 5 factorial is 5 times 4 times 3 times 2 times 1, which is 3 factorial. So those cancel. And that's a 20, that's 27, negative, so minus 2, 5, 40 is what you need. Which, if you had the extra time and you're really good at differentiating, and you did this 5 times, you would get the same thing. but that would take more than 5 times as long. Okay, that's it. See you tomorrow night.
For the exam, we said we'll be given the Taylor series for the time. Yeah, if we need, yeah. Or is it going to be given in the power series form, or is it expanded form like we did on the exam? Okay. Okay. We can run. Okay. All right. Thank you.
I have a question on the last problem. It says, so 6 multiplied by, we multiplied by this x squared. Wouldn't the actual term that has x to the fifth in it now be x to the 7th? So it's always the x to the one x to the fifth will always be the fifth root.
Yes, whatever is in front of it must be, it's not just the fifth derivative, it's the fifth derivative over 5 times 4. So you count it last, this side is 14, it's 7, it's 7, even though this doesn't look like it. But again, if you carry this out, morning, eventually it turns out to be that. This over that is equal to the coefficient here. Yeah, that's what I mean.
Do you mind moving over to it?
I'll get out of here. I want that. And I know from the individual term. So I'm start counting here and see this question. From that amount, this, right? I thought the x. Let me cut up and then we'll hold outside.
That'll give us enough time.
Any other questions?